right, now
Okay.
it's letting me unmute.
Here we
Thanks,
go.
thanks so much.
Hey.
All right, thanks so much for the kind words, Joe, and great to be here. And yeah, as Joe said, I'm calling on the road to customer offices. Yeah, life of a startup. But really, really excited to be here and to hear the talks I'm going to be listening. Um, yeah, so quick about Copilot. Copilot makes the user interaction layer for agents. So for building copilots, which are user interactive agents as opposed to autonomous agents, our mission is to bridge human and artificial intelligence. We believe that for the foreseeable future, the set of tasks that humans plus AI can tackle is far larger, more interesting than what just humans or just AI can do. And of course, we're going to hear today about some of the limitations of agents, in addition to all the obviously promise. And Yeah, we think having a human in the loop is one of the ways to take these systems that are incredible and amazing, but not yet able to go to production in most situations. Actually, bring them to production. You have essentially you work alongside this colleague um, that is better than you at some things and worse than you at other things, and together you can really facilitate amazing interactions. And specifically, we think that what's currently happening in the world of developer tools, right? We have Cursor and Windsurf and all those is going to come to product management software and insurance providers and tax assistants and all of those. And we're essentially building the infrastructure facilities at scale. We're open source, have over 18,000 GitHub stars, tens of thousands of installs per week, serving anywhere from hackers to top Silicon Valley unicorns to Fortune 100s. And yeah, essentially if you're building user interactive agents powered by either any of the agent frameworks, support LangGraph, CrewAI very soon. Literally next week or so, Mastra AG2 and a bunch of other ones as well. You can use us, or also for folks who don't use any agent framework at all. Yeah.
Amazing. Thank you so much. We'll get started with the paper now. Mert, over to you.
Sure. Let's see. Can I share the screen for some slides, maybe?
Yeah, you should be able to.
All right. Great. Uh, um, Great. You can see the presentation, right?
Yep.
Perfect. Oops. Yes. Hello again. Yeah. Once again, hello everyone, and thanks for inviting us to the seminar today. And yes, in this work, we essentially investigate why do multi-agent LLM systems fail, and hopefully we propose a taxonomy to categorize why would multi-agent systems fail, and what can we do about them. So there's a lot of hype about AI agents lately. Lots of startups being found near AI agents, but also in academia, um, the investigation of multi-agent LLMs, and how can we make AI agents scale better with test time compute resources. That is to say, if we have more time and budget to spend at test time, what can we do? How can we increase the performance of these agents? How can we do essentially a search space over the solutions more efficiently? Um, but before going more in depth, first it's good to define what is a LLM agent. So the first thing is, of course, that there should be a base large language model. But on its own, an LLM is simply a statistical machine that tells you what the next word is, given all the preceding words. Um, so this brings us to the important issue that while the next token prediction is super dependent, highly dependent on the prompt, So the prompts essentially define the LLM agent. You can use two different large language models, but you can give very different prompts to cause two very different outputs. But also, an agent needs to take some agency in the sense that um, the tasks we investigate are mainly coding tasks, where agents actually write a piece of code, or for example, browse on internet, go search for your queries on a browser, etc. So they need to be able to be equipped with tools to take these actions. This is what you really call by agency. And why would we have multi-agent LLMs? The thing is, when we stick such multiple LLMs together, they create a collective intelligence, and the interagent communications these agents um, do can make this overall system much stronger. More specifically, when you have a complicated task, decomposing that task into multiple components can be very useful. But also, um, the uh, in terms of having the task be processed more efficiently, um, multi-agent LLMs can also be used in terms of, for example, this MPI or Spark-like works where you can have parallelism and high performance. Also, um, again, in very long tasks that are probably challenging for a single agent, having multiple agents that are specialized on different topics perhaps allows you to have context management and diversity among agents. It's also an ensemble of specialized models, and for sure, like there's another vision that in the near future, as small models get better and better, people will start having their own agents in their edge devices. So having multi-agent systems and having them cooperate with each other can be helpful for context isolation and security. With all those benefits being said, we still find that the most popular these open source multi-agent systems continue to fail, and this brings the question. So these are this is like six different multi-agent systems um, tested across some various benchmarks. Um, but yeah, given all those benefits, they still exhibit lots of failures. So this warrants the question, okay, what can we do about them? Or precisely the need to understand how they fail so that we know what to solve for. So to tackle that question, we developed this taxonomy. Um where we identified 14 different failure modes grouped under three different categories: specification issues, intelligent misalignment, and task verification. And in the next, uh, I will talk a little more in detail about how to come up with a taxonomy. But should I take the questions now, or but yeah, yeah, you can feel to interrupt at any moment. By the way, it's perhaps easier for you not to forget any questions and save until the end. Uh, but if there are none so far, I will just proceed.
Yeah, we'll save questions for the second half.
Okay, let's do that now. Um, so yes, so in the previous slide, I was talking about we had a taxonomy, but now let's discuss how to come up with a taxonomy um, at all. So the first thing to do it is collect traces and then identify the broad failures in those traces. When we say a trace, what we really mean is a system log. Um, of a multi-agent system. So when you have multiple agents talking with each other, they talk with each other in natural language. So we log the inter-agent communication, but we also log the agent to environment communication. That is to say, for example, if they are solving a math problem, it is a math, like it's a solution they are giving, or if they are solving a coding problem, it is a piece of code that the agents wrote. So agent to agent communication, but also like telling each other what to do, and also agent to environment communication. Um, and to do this in a somewhat principled way, we adopt this approach called grounded theory, which is um, mostly borrowed or inspired from social science studies, where we collect data from 5 different multi-agent systems listed here: MetaGPT, ChatTab, HyperAgent, Upvolt, and AG2, and then we test them on different benchmarks, and then we identify various failure patterns that we observed in these systems. And to do that, we have human annotators read the traces to identify these failures. But after um, identifying those initial failures in a in a bunch of multi-agent system traces, in particular more than 150 traces, uh, we come up with an initial taxonomy. But once you have an initial taxonomy, which was different from the one I showed before, uh, you need to make sure that the taxonomy is valid and sound. And one way to make sure of that is um, to make sure that when different people read the taxonomy, they understand the same thing. What does that mean? So we provide a list of failure mode and their definitions. Now, for example, if I read a trace and annotate the failure modes using the taxonomy, and if, for example, Elena reads a trace and then annotates the taxonomy, errors there using the taxonomy, our conclusions should match if the taxonomy is very clear. So to test that, we conduct inter-annotator agreement studies, where in inter-annotator agreement studies, what essentially happens is that we collect a subset of traces, and then we have different expert annotators, and then they use a taxonomy to annotate the failure modes in the system. And in the first round, what really happened was the disagreement was a lot. So they sat down together, they discussed why there are disagreements, and then uh, improved the taxonomy. That is to say, changed some failure modes, deleted some failure modes, added some new failure modes, merged some failure modes, etc., until they reached consensus. Now, this is like a learning procedure in the sense that after these revisions are made to the taxonomy, we collected another set of traces to once again do another internet agreement study, and then we were actually quite impressed by the new uh, agreement reached there. And the way we precisely quantify agreement is through a statistical metric called Cohen's-Kappa score about iterator reliability. And we did, yeah, after achieving a good Cohen's-Kappa score in second round, we again did some more revisions, and then we did a third round of inter-rater agreement, and then yeah, after again having a good Cohen's-Kappa score there, we said okay, the taxonomy is finalized, and we were happy. But on top of that, one thing we also wanted to do is that so actually these multi-agent system traces can be very long, and having a person sit down and do this do annotation by hand using the taxonomy can be very arduous. So we said, okay, wouldn't it be very cool if we had an automated way to make these failure detections? So to do that, we developed an LLM as a judge pipeline, where essentially we have the large language model equipped with the very detailed descriptions of the failure modes in the taxonomy that we finalized as a result of the intermediate agreement studies, along with the examples, in context examples of how different failure modes might arise. And we also validated that automate LLM as a judge, again using intermediate agreement studies, this time between the LLM as a judge and humans. So this is the final taxonomy that we have under 3 different categories. So let's dive into these 3 different categories more in depth. These are specification failures, intelligent misalignment, and task verification. So what is specification issues? So this is a type of category that includes failure modes related to poor specification. Usually the ones that arise during the pre-execution or early stages of execution. And the failure modes specifically here include disobeying role specifications, disobeying task specifications, step repetition, conversation loss, or agents unaware of termination conditions. In a particular example here, we have a CEO agent and a CPO agent. So in multi-systems, it is very typical to have like to have them simulate a software company where the CEO is supposed to break up some tasks and CPO is supposed to verify, CPO is supposed to make sure that the product is meeting the constraints, etc. So, but here what happens is that the CEO essentially is a superior officer and needs to terminate the conversation when it's happy, but CPO takes over and then terminates the conversation abruptly, disobeying its role specifications. Another big failure category we have is called interagent misalignment, where in interagent misalignment, we have failure modes related to coordination of agents in a system. And these type of failure modes essentially arise during the execution stage of the task. So yeah, different components are conversation reset, failure to ask for clarification, task derailment, information withholding, ignoring other agents' input, and reasoning action mismatch. For example, here, this is an example from the app world environment where there's a supervisor agent and then there is a phone agent and that's supposed to execute some task. The supervisor agent asks the phone agent to log in with username, which is an email address, and then provides a password. However, the phone agent tries to log in with the phone number instead of the email, which is quite problematic because it's essentially phone agent ignores supervisor agent's input and causes the tasks to fail. The last but not least category is task verifications. So in multi-agent systems, verification has paramount importance because most of the multi-agent systems essentially claim to be powerful because they have a verifier agent that's supposed to do some quality assurance, some quality check. However, we see that most of the systems suffer from the verifiers essentially being useless. So they're either if there's a verifier, the verifier is usually incorrect, or sometimes there is no verification or very insufficient verification. And sometimes even the whole process ends prematurely because the verifiers that's supposed to check whether the end conditions are met aren't doing their due job. So, for example, an example here showing a useless verifier is this. The user here, which is the human, wants a chess game with inputs like KE8 or QF7. So if if you know chess, this is the formal chess notation, really. For example, qf7 means that the queen goes to tile f7. Here, for example, here, like doing a checkmate. But the AI agent designs a game saying that, okay, I designed a chess game, but the inputs are x1, y1, x2, y2, which are the input and output coordinates of the game. So technically the game runs, but this is not really what the user wanted. So, and if user thought, okay, the game is well working as I wanted, and enter QF7, for example, as an input, then the game would crash. But the verifier looks at the game, says that it runs and it looks good, so it passes its checks, resulting in an incorrect output essentially. So having introduced these failure modes and categories, you might say that, okay, like what about the co-occurrence of some failure modes? And that would be a great question. Indeed, some failure mode, we did some co-occurrence analysis of failure modes. Indeed, there are correlations between some failure modes, and it is very interesting to see how different failure modes would interplay with each other. Because, for example, in the first failure category, we have something called like disobeying task specifications, and here we have this like we the chess example can also be is also an example of disobeying task specifications because yeah, they are not met. Um, so for example, incorrect verification and this task specifications can go hand in hand a lot. But yeah, we see that all the failure modes are necessary. In fact, they're like the co-occurrence ratios are no more than 65%. So yeah, uh, but it's fun to see how they interplay with each other. Now, finally, let's go to the last part of the talk where we discuss why does it matter? Why does mass matter? So we can use essentially this taxonomy, which we name mass, to have better multi-agent systems. And to do that, the fine-grained analysis of what goes wrong with your multi-agent system. Let's say, yeah, you have a company providing multi-agent system solutions. Now you have some problems, with your task execution, but you are not really sure what to do. Like which components of your multi-agent system are failing or really causing the errors. Um, and essentially, this taxonomy gives a fine-grained analysis of what goes wrong. And we propose some tactical approaches that essentially are somewhat more straightforward things you can try based on the task at hand and your multi-agent system. But also there are some structure, and the tactical approaches will be improving the topology of your network of multi-agent systems, or making the prompts simply better. But also there are some structural strategies that should be done that are more uh, robust, such as having comprehensive verification and standardized communication protocols. And indeed, using, for example, MAST as a debugging tool, on the left-hand side, we first did a failure mode analysis on ChatDev, and then sorry, the one on the left is with HE2, the one on the right is with ChatDev. And then based on the failure modes, we try to first improve the prompts of the system, and then we try to improve the topology of the multi-agent system network. And as you see, these two tactical approaches cause a noticeable decrease. At least this decrease is captured by MAST. However, it is good to note that these tactical approaches, even change of topology, didn't fully resolve the issues, so more structural solutions are needed. So in conclusion, system design is crucial. Having just better single LLMs won't like give us AGI. Um, because yes, even though single LLMs can get better and better, when you have a system of them, where you attach basically multiple of them, the way you build a multi-agent system and the communication protocols, the topology, they all matter. And verification has paramount importance. And to that end, MAST is the first multi-agent failure taxonomy out there, and we really emphasize its utility as a practical tool for developers, and we provide a roadmap for future research in the area. And yeah, thanks a lot for listening to our talk. We recently like on Tuesday, we'll release a new version of the paper. And we also open sourced fully our code and data sets using the experiments. So yeah, please feel free to reach out to me or my colleagues, and happy to take any questions.
Oh, amazing. So we'll jump into the questions then. And the way we do it is you'll see me asking you to unmute. And sometimes I'll give you a heads up if there is time. So maybe we'll start with Joe, since you're off mute already and you have an amazing question you're asking, and then I'll message someone else. Joe, are you on mute? Oh, you're on mute. Okay. How did that happen?
Okay, there we go. All right, sorry.
There you go.
Yeah, so I mean, a quick question maybe is what in particular about multi-agent was interesting for your research? Because from my perspective, building agentic systems, whether it's multiple agents or one agent, it's more like a function of agency and autonomy that creates these problems. So my question is, what new problems arise, what unique new problems arise simply out of multi-agent, and what was your interest there?
Oh, thanks. That's a great question. So, okay, on a grand scale, okay, okay, I'll give you two different answers. One of them is that on a grand scale, in this paradigm of we can make LLMs reason better, multi-agent systems is like a generalization of the whole paradigm in the sense that, for example, one way to make LLMs to reason is using chain of thought prompting, where the agents essentially list their thoughts and then try to refine their own thoughts. But instead of having a single agent do that, you can have multiple agents debate the topic, and like discuss each other's solutions along with their own um, internal thoughts. So that's one thing. Very similar to that, you can have algorithms, a single agent algorithms like Monte Carlo tree search or best of n. But again, if you have a chance to instantiate multiple agents, you can just let them discuss the topic, debate the topic, and then you can, for example, do a majority voting out of them, which would be a generalization of best of n, rather than using a single agent. That's one thing. Another thing is, in my undergrad, I was doing more theoretical research on multi-agent systems without any LLMs at all, in the sense that, let's say you have a network of agents trying to make some decisions about real world, where it can be very hard for a single agent to receive all the necessary information to make an informed decision. So this is really coming into the area of hypothesis testing, where different agents aggregate their observations about real world to make some decisions, and in specific cases where every agent has a partial information that is insufficient to make a good decision. But when you have a group of agents together, like as a collectively, they have sufficient information. So yeah, lots of kinds of interesting problems arise there.
Okay, so I think you're saying
Amazing.
that in multi-agent systems, you get these theoretically more interesting to study because of these properties, and then practically more interesting because we've seen research results that show that multi-agent approaches work better. I think the third I would add is I think as the market evolves, the commercialized agents that are really good at their jobs will have proprietary data and proprietary techniques. And I'll want to use those in my overall system. So therefore, I have to be multi-agent if I want to take advantage of those.
Yeah,
The second
definitely.
question I had was, see if I could remember it. Oh yeah, you pointed out these ways that if you're figuring out the common fail patterns and then you're suggesting the ways to remedy those situations. My question is, are you seeing in your research yet it seems to me that there would be another agent that just does those two roles, and that would be a natural thing to bake into the agent framework. Is that happening?
Can you repeat your question? Maybe I just want to make sure I get it right.
Sure. So you've studied multi-agent systems, and then you've said, here are the fail patterns, and then here are the interventions to make an improvement, right?
Yes.
So I'm saying it would logically extend that these frameworks that are agent frameworks would utilize those two aspects, these sort of understanding of a failure and then the intervention to improve upon it as another agent in that system. And it should be just part of the agent framework. And I'm wondering if empirically you're seeing any research in that area or anyone building that into their agent systems.
Yeah, thanks a lot. So this is a very interesting topic. So I see. So having so the paper like the overall paper is I like say released quite soon. Like so it's quite recently. So we haven't seen anyone else do it. We have some friends who pursue that direction, who started pursuing that direction, and there's some interesting work in there where you essentially have an overseer agent that basically uh, is a, has the ability to like spawn new agents, like do some design decisions on the multi system as a whole, and that uses the taxonomy as a debugging tool, as you said, to make better choices. But yeah, it is too early to say conclusion results from that line of research, but it's a quite interesting one.
Right. Alnor, do you want to go next? I will unmute you.
Okay, can you hear me?
Yep.
Okay, perfect. So a lot of the paper that I read this morning kind of talked about your methodology on coming up with the categories and the stages. I'm wondering, what did the annotators, or what categories or stages did the annotators not come to consensus on? Was there anything interesting you can share there?
Sure. So okay, the version of the taxonomy seen here has very good consensus properties. But in the earlier versions of the taxonomy, the kind of problems we had were about, for example, we first had for example, we had to disambiguate between these two different kinds of failure modes, incomplete verification and incorrect verification, because it was not because some multi-agent systems have a verifier that is essentially useless. Some multi-agent systems do not have a verifier at all. And at the end, it is now obvious that to us that we should have two different failure modes for those two different cases, but it wasn't initially the case where we had something called weak verification and something as like non verification. but yeah, what does it mean for verification to be weak, etc. So yeah, this was one case where in different annotators would disagree with each other. Another case is that, for example, we had a misalignment case here that we decided to omit, which was called I'm just trying to remember the name. I think it was called something like task ambiguities, or interagent like communication ambiguities. But the problem with that was that, okay, for example, that failure mode was too vague that even if annotated, it didn't really tell anything to the developer because we push that mask should be used as a debugging tool, right? So every failure mode here, for example, essentially implies a certain solution idea. Yeah. Um, but uh, when we had that like interagent communication ambiguity as a task, as a failure mode, uh, we saw that, okay, some annotators annotate that, some annotators don't annotate that. But would it even matter if we just omitted that out? And it seemed like, yeah, we could just get rid of it without losing anything, and making the, let's say, information conveyed almost the same.
Okay, cool. Thanks.
Great. There was a question here about MCP with lots of pluses next to it. What do you see MCP as a solution to this problem?
Hmm. Mm. So, I haven't, okay, so I know what MCP is, to some extent. I haven't actually, played with, let's say, coded with it, but, to my understanding, MCP is essentially what TCP is for networking, in the sense that it gives a protocol for multi-agent, sorry, for agentic communication. Um, However, maybe it would help with, um, for example, context management here. Um, in particular, like it can make like role specifications of agents better. But I don't think, like, for example, a big part of the problems is task verification. Another big part is like agents not following each other's instructions or advice. And I don't think MCP would really be a solution to those. But it seems like a useful kit.
Yeah, yeah. There was also A2A. Someone's hoping here that will solve interagent comms with that. Google's new offering.
Actually, so we haven't experimented with A2A, but yeah, again, A2A, like now A2A again with might help with some tasks, some problems with in the middle category for agent coordination. But like regarding, for example, step repetitions or conversation management systems, I'm a little skeptical.
Great. So there's a hand from Tuesday. Please go ahead and ask.
Thank you. Thank you so much. If you can hear me, precisely this little breakdown that happened here about the question is been fundamentally the part that I find the most challenging, which is just definitional challenges and why we're asking a specific question. So the way that I was sort of looking at it, and I'd be fascinated to hear your perspective on this, especially when it comes to inter-annotator disagreement, because in the lab, I can statistically look at the rates of disagreement, but ultimately the perception to the person or the user broadly, the reason why we're testing them or why we want to make them safe, it's like I'm not even interested in arguing anyone to get on board with my idea that model context protocol is a solution. I'm just confused what we all thought the problem was. And from your perspective, when there's a point of failure, it's almost like to me, it's more confusing to figure out at what point of failure the actual error happened, and then at what point did everyone sort of not agree or look at it as you mentioned that the annotators, some people would say would note it and then other people wouldn't. So how does the human annotation, how did it affect the rest of the evaluation for you on your end?
Thank you.
I see. Uh, mhm. Um, mhm. So the thing is, so okay, let me try to give an answer, and then you can, yeah, I would appreciate a follow-up if it's not clear enough. So for us to claim that we have a good, so um, okay, when coming with a taxonomy of why multi-agent systems will fail, there are two important things. First, it should be general enough to be applicable to different multi-agent systems. But it should also be specific enough that for a single multi-agent systems failures and traces, it should give insights into what kind of solutions people might develop. Now, in that regard, when you have having something that is both generalizable but also insightful um, is hard in the sense that we need to have very clear definitions of what different failure modes are, such that like we need to somewhat make sure that when you have a multi-system trace and you try to figure out what the problems are in that trace with the taxonomy, like the conclusion should be more or less the same, regardless of who annotates it. Um, this is why inter-entity agreements were like has had paramount importance in making sure that we had a clear taxonomy.
Thank you. Ben, do you want to jump in?
Sure, thank you. Yeah, so my question was about assignments or tasks that technically succeed, but the business logic is not what was expected, right? And this is sort of an interesting state for agents, right? It's like, look in the database and read record 123, but if record 123 doesn't exist, they'll return and say, hey, I have an error there, but they did the job right. How do the evaluators consider that? And how and is there like a term for that state that you're using, a term of art?
I see. So okay, that's I think a very meaningful question in the sense that uh so there were a number of companies that reached to us after we made our paper public, and uh apparently the real problem in multi-agent systems, especially in enterprise, is data handling, like you said. Um, but at least in academia, the main examples we looked at are coding or math problems, where we have access to clear, um, like the problems are clear and the correct answers are clear. If you have a math problem and I have a multi-system trying to solve the problem, well, the definition of a failure is very easy, right? The answer is either right or wrong. Or for example, if there's a piece of code that I want the agents to do, after the agents write up the code, uh, we just run the code. If the code runs and passes the unit tests, uh, some edge cases, then it's fine. But if the code crashes or if the output of the code is not what we wanted, then it's a failure. So yeah, for math and coding, these were somewhat, let's say, more principled to check, to categorize what a failure is, but it's definitely a problem worth investigating what to do for more diverse real world tasks like data handling, as you said.
Great. Brett, you're next.
Yeah, hi. I wanted to get your sense, or maybe an opinion of yours on negative prompting. For much of the work that I'm doing right now, I find that people that are new or tinkering around me at work, they still kind of default to this notion of I can control attention and scope of the job to be done if I just add a negative prompt onto this. And it was triggered by one of the recent announcements from OpenAI where they said, I think it was 4.1 or 04 had 100% adherence to instructions, including negative prompts. And that kind of blew my mind, but just wanted to get a sense of whether or not you've seen anything and have an opinion on how to appropriately use that as a tool.
Maybe can you clarify a little bit what do you mean by negative prompts?
So if I were to give an agent a role and a job to do, and then I start to see that it's not doing it perfectly, the first several times, and it kind of goes through its loop, I then, as an end user, might think I can tell it not to do that one thing. And then I just add to a growing list of don't do this, don't do this, don't do this under that role instruction.
Yeah, don't use the word delve.
Yes, some of those things where you're trying to do the negative instruction, but sometimes that does not work quite as expected in LLMs.
Uh, that's very interesting. So, uh, actually, like in the multi-systems we investigated, for example, at the beginning of the talk, Atay mentioned that like they have a human in the loop system. So we don't have a human in the loops in any of the multi-systems here. So, like if the system does something that we don't want, we don't go back and say, okay, like don't do this, don't do that. Uh, so and the prompts are really like different agents in the system have different system prompts along with the um messages what they communicate to each other, whatever they are. Um, and yeah, that's really it. So we don't have experiments with negative prompts.
Okay, all right.
That could be your next paper
Yeah,
where
maybe.
you just do a bunch of negative prompts and see. Lee, do you want to go next? I will
Thank
unmute you.
Sure. Thank you. I had a question about grammars. Oftentimes, you can constrain whatever logits of an LLM to be in a specific grammar.
Mhm.
For example, if you're trying to generate JSON, you can only kind of produce logits that would make valid JSON. And there are ways to generalize grammars to basically any context-free grammar. Is there a role for grammars in a multi-agent system to constrain the response to be something, or is there even a role for like a small BERT classifier if you're expecting some list of three items, for instance, then you would train a classifier to say like this is a list of three items and this isn't. What is the role in your mind of grammars and other uh, workflows similar to that? Thank you.
I see. Yeah, thanks for the question. So The thing is in this work for multi-agent systems, we use like really powerful large language models like GPT-4o. So they usually don't have problems with adherence to grammar. Like I was also doing some NLP research in 2020 in undergrad, and back then having models output correct grammar was very problematic. But since I could say like GPT-3 and then moving forward, the grammar abilities of these powerful large language models are quite impressive. So we didn't really feel the need to use let's say grammar correction or like a classifier. Um, and yeah, and since we don't and since the output product we expect from these systems are like piece of code or stuff, we didn't really yeah we didn't really worry about grammar, but yeah, thanks for the interesting point.
Great. Devang, do you want to do last question?
Yeah, I had a question on privacy. Basically, have you observed any specific failure cases where LLM agents unintentionally leaked sensitive task information to other agents or users?
I see. So this is very interesting. Yeah, so we had LLM agents ignore each other's inputs, but we didn't really test cases about privacy. Uh, but that's a very interesting research point, I think. Yeah, both I guess research and I suppose of commercial value. But yeah, we haven't looked at privacy preserving situations.
Yeah, that's a whole new field of research.
Yes, certainly. It's very important.
Amazing. Well, we're going to wrap up very soon. I just wanted to thank everyone for joining us, and a big thank you to Mert for presenting and answering so many questions. We were able to get them in. We'll try and share the recording eventually. We're traditionally hasn't been an amazing, fully thought out way to do this. So please join live sessions. And yeah, please join the next one in May, where we're talking about risks in a lot more depth. And those in Toronto, I'll see you tonight because we have a big event at Shopify later. And yeah, very big thank you to our sponsor again for supporting this. If anybody wants to sponsor one of the future sessions, please talk to me or Joe. And Joe, do you want to say a few words?
Yeah, thanks for coming. As always, we look for feedback. So any suggestions you have to make these sessions more valuable for you, we want to hear it. Any suggestions for researchers to invite, or if you know any researchers or if you know any sponsors, that's always super helpful. In addition to Toronto, believe it or not, there's 10 other cities also doing meetups tonight around the world. So that's a very exciting milestone for AI Tinkers. I hope you can join one of our groups in your city or get a chapter started.